In this video, we're going to do another proof example. Okay, so I want to begin by stating a theorem which is going to be relevant in our example. So let's let A and B be n by n invertible matrices. Then the first part says, if you take the inverse twice, you just get the original matrix back. In other words, the inverse of A inverse is just A. The second property says, if you form the product and look at A times B, that is invertible. And moreover, the formula for A times B inverse is B inverse times A inverse. So you take the inverses of both of them and you switch their order. And then finally, the third property says the transpose is invertible. So the transpose of A is invertible if A is invertible. And moreover, the inverse of A transpose is the same thing as A inverse transpose. Okay, so I'm going to prove the second of these. I'm going to prove that A times B is invertible by showing that this is a formula for A times B inverse. Okay, so how will we do this exactly? What does this look like? So what I'm going to do is I'm going to compute. I'm trying to show that A times B is invertible. And the way I'll do that is I'll multiply it by some matrix. I'll multiply it by some matrix to hopefully get that this equals the identity, In at the end. Okay, so let's multiply it by B inverse A inverse. I'm trying to show that that is the formula for the inverse of A times B. And the nice part about doing this is when I multiply, so I have the A, and then B times B inverse, that becomes In. And then I still have the A inverse. And then if I multiply A times the identity, I just get A. So I have A times A inverse. And A times A inverse equals In. Okay, so at this point what we've shown is, we've shown that AB, that matrix, times this other matrix, B inverse, A inverse, equals the identity. So that shows that these matrices, this is the first one, and this is the second one, are inverses of each other. Okay, so this proves property 2. Okay, so we are ready to take on this example, this next example, this proof problem. So A is 3 by 3, and the transformation, that maps a vector x to A times x, that is onto. So the transformation associated with A is onto. And B is a 3 by 3 matrix as well, and the columns of B are A times the vector 1, 0, 0, A times the vector 1, 2, 0, and A times the vector 1, 2, 3. And I want to prove that B is invertible. Okay. So just like we did in the last video with the proof problem, let's begin this by doing some scratch work and identifying, so scratch work, and let's identify what it is that we know and what is it that we want to show. So WTS was my abbreviation, again, remember, for want to show. So keep in mind what it is that I know and what it is that I want to show. So what I know is that, well, I know that A is 3 by 3, and it's onto. So we know that it's onto, so that may be important. And the other thing that we know is, we know something about B and what B looks like. So B is a matrix. So one of its columns is A times 1, 0, 0. The next column is A times 1, 2, 0. And the next column is A times 1, 2, 3. Okay, so let's squeeze that in there. Let me give myself a little bit more room here. Okay, so that is the end of the matrix, and let me put this line to separate what I know from what it is that I want to show. And what I want to show, my goal, is to prove that B is invertible. Okay, so far I haven't written down anything that was not given to me in the problem. I've just identified what it is that I know and what it is that I want to show. So it's really important with proof problems in particular to think about these questions on your own for a while. So at this point, I want you guys to think about this problem for 2 minutes, at least 2 minutes. Pause the video and think about it. Okay, so 4, 3, 2, 1. Pause the video and think about it for at least 2 minutes. Okay, so hopefully you guys have done that. Hopefully it's been about 2 minutes for you. Just a few seconds for me here. Okay, so what I want to do now is I want to think more about what it is that I know and what it is that I want to show and how I can connect these. So I know, for example, that A is 3 by 3 and it's onto. The fact that it's onto tells me that there are pivots in, let's put this in a different color actually. There are pivots in each row. Pivots in each row. And if there's pivots in each row and my matrix is square like this, it's 3 by 3, that tells me that A is invertible. A is invertible. That's the invertible matrix theorem that tells me this. Okay, that's pretty nice. From the fact that A is onto, I now know that A is invertible because it's square. Pivots in each row tells me there's also pivots in each column because, again, it's square. Okay, so I know something very concrete about A. I'm trying to show that B is invertible. Well, what do I know about B? I know B is written in this form. One thing that maybe we might recognize is this form for how B is written is actually the original definition of matrix multiplication. This is actually the same thing as writing A times the matrix that has columns 1, 0, 0, 1, 2, 0, and 1, 2, 3. The original definition for how we multiplied a matrix A times another matrix like this was we multiplied A times the first column, and that became the first column of the product. And then A times the second column, and that became the second column of the product, and so on. That's how we defined the product before the row vector rule. Okay, so now we know that B equals A times this other matrix. Well, we know that A is invertible. So it would be really nice if this other matrix was invertible. It would be really nice if that was the case. Okay, so I'm going to put that in the want to show column. I want to show that the matrix 1, 0, 0, 1, 2, 0, 1, 2, 3 is invertible. Because if it was, well, A is invertible, and it's multiplied by another invertible matrix. And we just stated a theorem above this that said if A and B are both invertible matrices, then their product is invertible. Okay, so what remains for us to show is that this matrix is invertible. But that is actually easy because I can see what the pivots are. So at this point, I think we're ready to write up the proof. Okay. So in the proof, I sort of began with what it is that I was initially given. So what we were given. We were given that A is onto. So since A is onto, and because it was also square, and it's n by n, this implies that A is invertible. This implies that A is invertible by the invertible matrix theorem. So if you didn't state the fact that, oh, this is true because of the invertible matrix theorem, that's probably okay. But I just wanted to be as rigorous as I could here. Okay. Okay, so the next thing that we did is we sort of wrote what B was. So let's do the same thing in my proof. I'm just going to do it with complete sentences to make my argument as rigorous as possible. So the first column was A times 1, 0, 0. The next column was A times 1, 2, 0. And the next column was A times 1, 2, 3. And just like we did in the scratch work, let's rewrite this using the definition of matrix multiplication. This is A times the matrix 1, 0, 0, and then 1, 2, 0, and then 1, 2, 3. Okay, so let's call this matrix something, just for short. Let's just call this C. Well, we wanted to show the matrix C is invertible. So the matrix C, which is 1, 0, 0, 1, 2, 0, 1, 2, 3, this is also invertible. Why? Why is this invertible? Well, since we can clearly see what the pivots are, since it has pivots in each row and column. This is already in echelon form. The pivots are the 1, this 2, and this 3. So when my matrix has pivots in each row and column, that means that the matrix C is invertible. Okay, so now we know that A is invertible, and we know that C is invertible. Okay, so now we can use that previous theorem. So by the previous theorem, since A and C are both invertible, since they are both invertible, that means that B, our matrix that we were interested in, B, which is A times C, is also invertible. And that's what we wanted to show. We wanted to show that the matrix B was invertible. So at this point, we are done with the proof. So I write my symbol with this box that's shaded in that indicates, oh, we are now done with the proof.